Assalamualaikum, my name is Nufara Amalin binti Yusri, a final year student of Bachelor in Chemistry with Management. I was supervised by Dr. Amira Amelina Ahmad Tarmizi. My final year project is about a review on the corrosion performance of polyaniline-silica composite on steel surface in acidic medium. The first one is the introduction. Polyaniline is a conducting polymer that is commonly investigated as an additive to standard organic coating for corrosion prevention of metallic substrate and act as an anodic protection that reducing the rate of metal corrosion significantly. PANI have a number of distinct advantages, but they also have a number of drawbacks. Because of its low processing capacity, inflexibility, and lack of biodegradability, PANI biological use are limited. Blending PANI with inorganic particles is a good way to create outstanding hybrid material that combine the inorganic component thermal resistance and mechanical strength with PANI electrical properties. Silicon dioxide can improve the hardness and adhesion of the corresponding hybrid to other polar polymer matrices and metal substrates. There are two problem statements of this research. PANI has a lot of potential for technical application, including as anti-corrosion safety, but it has yet to be proved if the PANI composite have any excellent properties that can prove their variability in other applications as well. The second one is a number of strategies has been investigated to solve the concern of PANI processability, with blending and compositing being the most widely employed strategies. So many researchers add filler, but yet only a few studies reported on silica filler blending with PANI. The objective of this research is to study the properties and application of polyaniline composite as a corrosion protection and to study the corrosion performance of two different types of polyaniline-silica composite on steel surface in acidic medium. Let's look at the properties of polyaniline. The first one is the physical properties. According to Nain et al. 2018, polyaniline is usually found in powder form and the color of polyaniline varies depending on the oxidation state. The second one is the electrochemical properties. Polyaniline exhibits good chemical resistance in acidic and basic solution that does not undergo any chemical reaction or chemical degradation. Cross linkage also produced at high temperature. The next one is the mechanical properties. The compact polyaniline powder pellet demonstrates excellent mechanical strength. According to Babel and Hiran 2021, dynamic mechanical analysis was used to investigate the mechanical properties of PANI, and the porosity and surface area of PANI film are both high. And the last one is the anti-corrosion properties. Polyaniline electrochemical activity can help with base metal preservation while also increasing corrosion current and speeding up base metal corrosion. As a result, high conductivity accelerates the penetration of cation. Therefore, PANI does not require to have ultra-high conductivity in the field of anti-corrosion and semiconductor because PANI already have excellent anti-corrosion capabilities. Let's proceed to the application of polyaniline. The first one is the solar cell. Platinum is the most expensive component in the solar cell. PANI is the perfect material to replace platinum because of its higher electrocatalytic activity and lower charge transfer rate for redox process. Microporous PANI electrode perform even better than platinum electrode. PANI porosity reaches the specific surface area of liquid electrolyte in solar cell that improving catalytic activity and trapping efficiency. For anti-corrosion material, polybenzodiazine (PBZ) have a low shrinkage, a low surface free energy, low water absorption, and good thermal and mechanical properties. PBZ protects steel on its own, but its combination with PANI outperforms pristine rubber in terms of protection. So PBZ was proved as a promising anti-corrosion use for carbon steel. In supercapacitor, PANI is one of the most favorable electrode material because of its high electrical conductivity and pseudo-capacitance. PANI also have a strong environmental stability, ease of synthesis, and cost effectiveness. The next one is the metal ion removal. PANI high concentration of amine group make it a promising choice for heavy metal removal. For intrinsically conductive polymer, ICP presents as a smart coating to protect defective area from corrosion by altering corrosion protection. PANI effectiveness based on polymer doping level as well as corrosive environment. The next one is the polyaniline composite. The first one is the PANI zinc. The zinc layer functions as a sacrificial anode to protect my steel against corrosion, while the organic layer works as a physical barrier. The electrical conductivity and anti-corrosion performance of polyaniline composite and nanocomposite as coating on iron sample have been tested using a simple solution mixing process. Corrosion experiment revealed that the anti-corrosion capability of polyaniline nanocomposite coating on the iron sample is thermodynamically and kinetically superior to pure poly coating. As a result, zinc nanoparticles have a favorable synergistic effect on the corrosion resistance of the poly matrix. The second one is the polyaniline aluminium oxide. The finding shows that the steel panel coated with polyaniline composite and aluminium oxide coating corrode less than the bare steel panel and sample coated with polyaniline and paint alone. The third one is the polyaniline silicon dioxide. The incorporation of inorganic nanoparticles such as silicon dioxide into a epoxy matrix improves coating integrity and strength while also promoting barrier properties for corrosion prevention. Corrosion tests revealed that the charge transfer resistance of nanocomposite coated steel was significantly greater than pure polyaniline coated and bare steel. Let's take a look on the methodology. There are three simple processes of the methodology. The first one is the synthesis of polyaniline silicon dioxide composite nanoparticle. The second one is the characterization, and the third one is the corrosion analysis. In situ polymerization was used to synthesize thallium trioxide silica polyaniline nanocomposite. In a study conducted by Abdul Latif and Khalaf of 2018, the produced thallium trioxide silica nanocomposite were immersed in 1.5 ml of dispersed aniline solution and 100 ml of 0.2 molar acetic acid, which was labeled as solution 1. The mixture was then cooled in an ice bath at 4 degrees Celsius. Solution 2 was created by dissolving 0.006 molar ammonium persulfate in 25 ml 0.2 molar acetic acid. Then, at room temperature, solution 2 was added dropwise to solution 1 and swirled for 12 hours. Silica dioxide polyaniline nanocomposite was prepared by a simple electrospinning strategy. In 20 ml of ethanol, 1.5 ml of camphor sulfonic acid doped polyaniline (PaNiCSA) solution was ultrasonic. Both of the nanocomposites use the same characterization method, which is Fourier transform infrared, scanning electron microscopy, and transmission electron microscopy. Thallium trioxide silica polyaniline nanocomposite use two methods for corrosion analysis, which is electrochemical impedance spectroscopy and potential dynamic polarization. Both approaches were carried out in typical true electrode cell, where carbon steel as the working electrode, saturated calomel electrode (SCE) as the reference electrode, and platinum sheet as the counter electrode. While only electrochemical impedance spectroscopy was used to investigate the electrochemical behavior of uncoated and coated Q235 carbon steel in a true electrode cell for silicon dioxide poly nanocomposite. Let's move on to the result and discussion. The first one is the FTIR analysis. For thallium trioxide silica polyaniline nanocomposite, the pure aniline interact with the pore of the SPA wall through a nitrogen atom, as evident by the substantial decrease in the strength of metal plate as shown in figure B and C above. The result of the low loaded metal ratio in the SPA 50 frame means there are no noticeable thallium oxide bands. For silicon dioxide polyaniline nanocomposite, the stretching and bending vibration of silicene band are responsible for the occurrence of peak at 1099 and 800 per centimeter. In silicon dioxide, FTIR spectra and SiOA stretching was represented by the peak at 943 per centimeter. The disappearance of some typical absorption peak could be attributed to the stretching vibration of silicene band overlapping. For the same analysis of thallium trioxide silica polyaniline nanocomposite, the formation of agglomeration of small irregular particles completely spherical with an average size ranging of 1.3 until 1.6 micrometer. For the high resolution TEM analysis, the funny morphology was defined as a tube structure produced without the use of surfactant or templates. The average inner diameter was 6 to 8 nanometer with the outer diameter of 24 to 28 nanometer. The same analysis for silicon dioxide polyaniline nanocomposite showed that the produced silicon dioxide was smooth sphere with the size in the range of 100 to 300 nanometer. For the TEM analysis, the silica sphere are spherical and smooth. Moreover, in the presence of polyaniline, the silicon dioxide polyaniline particle display mild deformation and their surface become rough. The next one is the anti-corrosion performance. For the EIS result, the polyaniline, the mass ratio of 5% and 10%, thallium trioxide silica polyaniline have maximum inhibitory efficiency of 87.24%, 92.50%, and 94.70% at 150 parts per million. The Nyquist plot diameter increased after introducing the polyaniline and thallium-3 oxide silica polyaniline nanocomposite to the corrosive media, indicating that the corrosion resistance of steel has increased. For the PDP result, the highest shift in the value of E-core corresponding to the plan was 90, 31 and 21 mV. The presence of polyaniline and thallium-3 oxide silica polyaniline composite on the metal surface acts as a protective coating, preventing contact with the corrosive media. The EIS result for the silicon dioxide polyaniline with the weight ratio of 4:1 coating have a greater resistance than the other silicon dioxide putty coating, indicating that the silicon dioxide putty with the weight ratio of 4:1 coating has the most challenging electron transfer process. Silicon dioxide polyaniline have a unique structure that encapsulates silica sphere in a polyaniline shell, which improve the mechanical properties of the putty coating. As a conclusion, polyaniline is the only conducting polymer whose electrical structure can be changed in a reversible manner due to the oxidation and protonation process. Furthermore, it is worthwhile to take a less expensive and less environmentally dangerous strategy by limiting the usage of toxic chemicals. The silicon dioxide polyaniline coating employed as carbon steel corrosion prevention coating have good hydrophobicity and anti-permeability. The hydrophobicity and good anti-permeability of the coating can reduce the number of corrosion products like blister and rust, as well as lengthen the coating life. Thallium-3 oxide silica nanoparticle may potentially serve as a physical barrier against corrosive ion. The coating outstanding barrier behavior and the creation of a thick passive layer are both important factors in its superior anti-corrosion performance. That's all from me. Thank you.